Yes, yes, indeed. So here, Oliver is going to open a retirement account and deposit $1,800 the first year. After that, he wants to increase his deposits by $100 each subsequent year. So what we're talking about as like the opening deposit, that's like year 0. So then like year 1, year 2, etc. So notice how they put it in the table already, as it's just like the starting amount, the year 0. So then in the first year, first full year after, if he increases it by 1900 or by 100, he's going to put in 1900. And then the second year, increases it by another 100, he's going to put in 2000. So we're going to fill in the table, and we're going to calculate the absolute and the relative change. So we've already got a couple numbers for our table. This would be 1900 and then 2000. And then what would the deposit be for year 3? Yeah, you got it. Yeah, sometimes life's that easy.
How heartbroken would you be if we all just said like 2005 or something? Not right.
Be like, okay, all right, let's back up. All right. So now I see Chris just wants to sabotage things just to see how I react. So the absolute change from the previous year, that just means we're subtracting. So how much did it change by? Well, how did we even get those numbers, right? We know he was going to do $100 more. And then to find the relative change from the previous year, remember that we would be using 100 over the earlier value, the one right before. So for this one, we're going to do 100 divided by 1800. We're going to leave it as a decimal here and then write it as a percent to the right. So as a decimal, I went ahead and left 3 decimal places so that when I move it over to make it a percent, I have like to the nearest 1/10 of a percent. Did anyone else get that same number if you did 100 divided by 1800? Okay, good. So the absolute change, still another $100. But now when we figure out the relative change, now it's 100 with 1900 the year prior as the base. So the relative change from the previous year, not from the very start. So it's just the $100 still, but over 1900. So we're going to see those decimals change. So we're just dividing. And then we're moving the decimal 2 places to the right, or you could multiply by 100 to change that to a percent.
Is that a 3, right?
053, yes.
Okay.
So then we have some questions below the table. How is the total amount of deposits changing from year to year? So increasing. So it's always going to be increasing by $100 more than the year before. Hello, that's not how you spell previous or prior. And which one is staying the same, the absolute change or the relative change? The absolute change is staying the same. So when the absolute change is staying the same, that means that this is linear. Okay, that this is linear, like what we talked about before. So without actually continuing the table, since the absolute change is staying the same, it is linear. So without continuing the table, if we wanted to know, when this says total amount, it means just during the 6th year, like what you're putting in the table, not adding all of them together, which I think the word total is a little misleading there. So we could think 1,800 plus 6 times 100, right? The 6th year is only a couple years away. I could easily add 200 to my 2,200 also. But if I said, what about the 16th year? Well, at the 16th year, then I could certainly go on. I could put a 16. So we could, this is linear. If I wanted to find any year since the initial amount, that's like our B, our starting point, and then 100x, I could write it in slope intercept form, which I kind of wrote it backwards from what I had up there, but.
What did you say about number 4 again? So it's not hard.
That the absolute change is what stays the same. So just when you look at the table, is the absolute column the same all the way down, or is the relative column the same all the way down? The absolute. So if the absolute change is the same, then it is linear. Okay, so if that stays the same, it's linear. And then that absolute change is the slope. And of course, the starting point is the B. So that part kind of ties into what we did previously. But now on the next page, we're going to look at, instead, he says like, well, you know, as I make more money, I could probably increase because my percentage that I'm saving is actually going down. So Oliver's decided he's going to increase his deposits by a certain percentage each year rather than a specific dollar amount. So as he looked at it, he noticed that $100 was roughly 6% of what he's currently contributing. And so he's going to increase it by 6% in the coming year, and then increase that by 6%, and so on. So if he increases his total retirement deposits by 6% in the first year, so if we're going to do 1,800 and he's increasing it by 6%. So it's not just going to be 6, right? I mean, it's not just going to be the 6%. So I could do times 0.06 to find out how much it's going up and then add it on. Or I can do a proportion. And I could even say 106, right? Because it would be 106% of what it had been. Or I can do just 6% and then add it on. We should come up with $1,908. So if I did it with a decimal, this would give me the increase. And then I would need to add that on to the 1,800. You could also
Just
do,
multiply it, and she need to put 1.06.
if I just want to multiply, yes. Yeah, I could, you're exactly right. I could do 1.06 and I wouldn't have an addition step. I could add the 100% then instead of adding it on. So that gave us the 1,908. And then now you could do this table in whatever order you want to do the table. But one of the ways I found it easy is if I just leave that in my calculator and then do times 1.06 again. So if I leave the 1908 in the calculator, times 1.06, then I have the next year, he's going to deposit $2,022.48. Notice it doesn't, like, it's not still based on the 1,800. Now we're doing times year one. And then we would take that times the next year. And of course, as it says in the directions, we're going to round the deposits to the nearest cent. And you could keep going down first, or you could go across to find out the absolute change. Now I would subtract those, or if I did times 0.06, that is that part. And then the relative change. Now I could do this 108 divided by 1,800. It certainly better come out to be 0.06. So go ahead and finish out the table.
For the 108 divided, you divide that by 1908, right?
No, you divide it by the previous value.
Okay, I'll keep it.
Yep, you're always dividing it. Yeah, you're dividing it by the old. Because the percentage was based on the prior year. So then when you do the difference for year two and get $114.48, that one is going to get divided by 1,908 because that is the base that was based on. That increase was based on 1,908. Now, occasionally your decimal might not come out exactly 0.06 because of rounding. It might be 0.059 something, but to the nearest whole percent should still stay. What were our deposits for year three? Oh, so that would be the absolute change, the 121.35. Yep. 2143.83. And yes, the difference would be the 121.35. And then for year four, 2,272.46. which gives our difference. And remember, the difference I can just subtract with the year before. Absolute change is just the difference, how much. And then all of these should come up to be 6%. Again, due to rounding, it might be 0.059 something, but now I really should be able to predict without dividing that they're 6%, because how did we get the numbers? We added 6%, right? That's how we got the numbers. We added 6%. So unless something went wrong with what I did, I should certainly come back to being the relative change being 6%. So to answer number 10, how are they change? Well, how's the total changing? What is a mathematical rule? So we're adding 6% each year. So that mathematical rule we could say is 1.06 is what we actually used, times the prior year. You could make the prior year X or whatever you'd like to do. So which one's staying the same here? Absolute or relative? Relative, obviously, right? So then without continuing the table, how could you mathematically find this? So any year actually, but the 6th year wouldn't be so bad. I'd have to do it a couple times though. If you take your starting amount and think what we're doing, we are repeatedly multiplying times 1.06, right? 1.06. How could we write repeated multiplication by the same number? Exponent, right? So if it is 6, then we would use an exponent of 6. So for our prior ones, we could have done 1800 times 1.06 to the 4th power, but because we needed the numbers in between, it was just as easy to use the prior number. And so if we type that in, by the way, you type that into the calculator, on our calculators in the classroom, that is your exponent button. For some of your phones, it might look like X to the Y or Y to the X for the exponent. And do not hit equal between the 1800, like do 1800 times 1.06 to the power. Don't press equal before you do the power, because that will give you a very, very different number. So I came up with 2,553 and 33 cents. And this is our exponential growth, basically. So we take the initial amount, the starting amount, the growth factor, which is the 100% plus the percent of change. That's why we have to have the 1.06. If we just use 0.06, we're going to get a much smaller number, and it's going to be like, this is not right. And then the exponent is how many times it's going through this. So the time period, like if it's year 6, sometimes things are monthly or daily or whatever, but how many times the interest or it's being raised to that power. Oftentimes I said interest because it's used for interest. And of course the percent needs to be changed to a decimal. I can't say like 1 plus 6. So 1.06. And so if we want to find the growth factor besides what we've already done, like we knew this was 6%, if we just had the table, then if we use 2 consecutive values and the new divided by the old, that would give us the growth factor. So saying that there's a relative change of 6%, or that the growth factor is 1.06 is the same thing. But the growth factor, like if I said there's a relative change of 106%, that would be a different meaning. That would be 2.06 as a growth factor. There's our problem we just worked out. And then there's Oliver's contributions. So this is not totaling them. This is just how much each year he would be putting in. Okay, so it's not his total money, it's how, because the total money would be an even greater difference here. So estimate the difference between retirement contributions at 35 years. So that just means look at what we have on the table. At 35 years down there where the dots stop, if we're using the exponential rule, looks like he's putting in about $14,000. And if we are using just the linear rule, maybe 5,500 is the estimate. So about $8,500 difference just in that 1 year of how much he would be saving. So if his annual contributions are broken across 26 equal deposits, so in other words, maybe he gets paid every 2 weeks and he's putting the money in every 2 weeks, how much would each deposit be? So now if I took my estimate of 14,000, divide it by the 26 deposits, would mean that each pay period he is putting in $538.46. So if that's a great plan for Oliver, that if he could do that and increase how much he's putting in, but if his pay is not also going up, he might find by that point he could be having a hard time putting aside that much money every pay period. It's going to be set up nice for retirement if you can, but. Right, so all the rest of these, we're going to keep using that exponential growth pattern where we're going to use the growth factor, which is going to be, if it's growth, we're adding to 1. So change your percent to a decimal and add to the 1. And then we have to think about, like, are we talking days, years, months, because that will change in some of these problems. So 1%. So then our growth factor, 1.01. And then in this case, the unit of time is years, but it's years past 2000. So like if we want the date, we would have to add to 2000 if we want the actual year. So that 2000 is going to be our starting point. So we've got our 6.2 billion. And if you can remember to write billion at the end, you could probably leave that off, but I don't trust myself, so I'm putting it in there. 1.01, and then you could call that X or T, but that's where your time gets plugged in. So that's this is the general equation. And then if I want for 2014, then that's 14 years after 2000. So we would use this equation or this expression with a 14 here. Now you can simply put 6.2 and your times 1.01 to the 14th, and then put the word billion on at the end. So 7.1 billion or 7.13 billion. Typically, since we were only given one decimal place, we would only return an answer with one decimal. If it does not tell you specifically where to round, like I would not mark it wrong. You could also tell me 7.13. If it specifically says to the nearest tenth of a billion, then please don't include 3. So 7.1 or 7.13 here is fine. So a number 2, Masters of the Universe. Anyone watch that cartoon, Masters of the Universe? Got an action. Yeah, so we got action figure, and it's like watching the prices, hoping he can sell this. It's like the price has still been rising. I'd say get rid of it while you can, before your kid gets it and tears the head off, and then you're not going to be able to. Anyway, so this says we can use 2 consecutive values to find the growth factor. So consecutive means one right after the other. So it doesn't matter whether I use 2014 and 2015 or 15 and 16. And we don't need to subtract since we're finding the whole growth factor. We just put the new over the old. So if I want to use those first 2 years, then I would have 248.68 over 227.67. Why? I don't know why. Was it disconnected? Okay. I was writing, but it wasn't right. Okay, then. Be that way. So I am, let's see, I got 1.092 or just 1.09, basically 9%. And the unit of time here, since these numbers were given just as a year, this would be year, so each year. So assuming that the trend continues, and this would be years past 2014.
You got that number for A by dividing the list price, right?
Yes.
227, 57, 271.
No, it has to be 2 of them that are next to each other. So it has to be consecutive. So it could either be 271.63 divided by 248.68 or 248.68 divided by 227.67. New over old, yes. Yes, you buy the more recent. So on the page right before this, growth factor in the gray there, growth factor equals new over old using 2 consecutive data points.
This really hurts me, right? Because can I tell a quick story real quick?
Sure.
So 3-4 years ago, I was up in Michigan hanging out with guys. We went to the comic book store, and I'm a huge fan of Alien vs. Predator. I got the 50th anniversary collector's edition complete issue 1, right? It's a little thick one. I got it, never took out the packaging, and then I was curious. Really, a few weeks ago, I looked it up on eBay. I got this for $50 on eBay. It's already up at $170. So I asked my buddy if he goes up there, go to the store and tell me the price of it in the store. It's still not even there. He said they weren't selling anymore, and I sent him a picture. He could look at it. And when I took the picture, I noticed that somehow it got a nice little scar on the top right, and now the plastic's torn, and I was just so upset. So I was like, oh, I mean, I might as well just read it now because there's a nice little dash. You can see the cardboard. I was upset. I was like, I can't believe, and I kept it in the drawer for the literally the last 3 years. I don't even know how it happened.
You're like, how did it get jacked around?
Yeah, I guess I should put somewhere so I just throw things in there, but it's like, that was at the bottom, so I just get.
Someone do just 1.09 and see what you get. I had left the 2 on there. So if you just did 1.09, you're gonna get something slightly smaller. How much? I don't think it should be 700 something. I think that's too much. Did you do 1.09, not 1.9? $227.67. Okay. Say. So if you left it as just 1.09, just for a whole 9%, then you're gonna get something, it's gonna be a little bit different. How much did you say, Jess? 453? And that came from the same thing, but just rounded with the 2 off there, so to the nearest whole percent. So then down in number 3, I have a whole bunch of stuff at my house, by the way, that I have saved that was my son's, that I, have these, like, maybe I could just like have an eBay day and go through. And my son has a lot of sports cards, and they haven't been worth nearly what they were at the time when he bought them, but they're not doing anything except taking up space in my house right now. So like, he was a big John Elway fan, so he has like 250 just John Elway cards. No, Muhammad, the question is supposed to be, did you guys do anything before I got here? As if I'm, when people are absent and they say, did you do anything? I'm like, yeah, you've been in my class before. Like, has there ever been a day we didn't do anything? Not what did you do, but did you do anything?
You're probably aware.
I knew you had a review yesterday, so I figured that you the test. We're on 9.4.
Wait, let's see, which number are we using? We're using the 460, the 430.
Well, see, I mean, you could write down either one. I just gave you both numbers.
Oh, okay.
Okay, because it would depend if you said to the nearest whole percent or you left it 1.092. So now we have different growth patterns in this table. There are 3 different bits of information: future, classic, and standard. Which one of those is exponential? Okay, so which one is exponential? So try to figure out which one you think is exponential growth. So remember, first off, that how we know if something is exponential growth is that the growth factor or the relative change would stay the same. The growth factor would be the same. If the absolute change stays the same, that means it's linear. So if it's going up by the exact same amount every time, if I just subtract, that's linear, so it can't be exponential. And then you could find your growth factor. Remember, at the top of 9.3, do a new divided by old using 2 consecutive ones. And then use 2 more consecutive ones to make sure it's staying the same. So if I do 20.38 divided by 19, write down a number, and then do 21.76 divided by 20.38. If those 2 numbers aren't the same, it can't be exponential. If those 2 were the same, I would keep going to confirm that all of them in that column, that it's exponential. that is not growth. It can be decay, which means it's going down. So things are dying off, not growing, losing effectiveness, like the amount of a drug in your system. So we find a decay factor, just like we had before we had a growth factor. So a decay factor is one, take away the percent of change. And decay factor, we can also find by using the new divided by the old. So we can still find that. We're just going to see that it's going down. That's what, so, but that's still how we're going to find our percent. And then what I wrote up here is just generally the rule, what I wrote on the board, that we start with that initial amount. That's like our starting point. And then it's either 1 plus or minus. If it's decay, it's going to be minus some percent. And then the time is the exponent. So here, if she loses 20% of 26% of their value, we're going to do 1 minus 0.26. So I'm doing 1 minus 0.26. So the decay factor is 0.74. And this is happening, the unit of time here is years. And then so our exponential model would be, she's starting out with 500,000. That's her starting point. And I'm going to use parentheses here, but you can just use time. So it just looks weird if I put an X there. And then 0.74. And then I'm going to use the caret because I can't make an exponent on here. And then if I wanted to know, I don't know how many years. So in the model, there's going to be something that you don't know. And then now if it's how many she has left after 5 years, then instead of doing 0.74 to find 74% and then doing it again and again and again, like how we filled in the retirement table, we can simply put the 5 where the X is. To come up with, after 5 years, she's only going to have 110,950 miles left.
Confused with the 1 minus 0.26 equals so many more. I feel like
What's $1 take away 26 cents?
okay, so
Yep. Does that make sense to you?
yeah.
Yeah, it's like the 100% take away the 26%. Indeed. All right, so if we look on the next page, we're gonna get to look about Lyme disease. Exciting stuff. So we have some antibiotics and some things about how long they stay in your system. If any of you have ever wondered, why can't I just take all the medicine once a day? Well, because it loses its effectiveness. So you want to keep it kind of at a certain level. And so that's why we don't want to just take like the whole dose, for the day at once. Different medicines are different as far as what stays in your system. So here, if it says hours since the last dose, and that's 0, the 0 time is our initial amount. So for number 1 here, these are 2 doxycycline and amoxicillin are 2 things typically given for Lyme disease. So what is the recommended dosage for amoxicillin? 500 milligrams. Why would you think it's 500 milligrams? Because that's at 0 hours. That's how much they're taking at the beginning. Exactly. So that's how much they take at the beginning is 500. So then, and then the recommended dosage for doxycycline, 100 milligrams. Again, that's what it is that's our initial amount. So then how much does amoxicillin degrade from hour to hour, and what is the decay factor? Mm-hmm. Okay, so how much does it degrade from hour to hour? Would be 50%. And the decay factor would also be 50% or 0.5. Because if I do 1 minus 0.5, it's still 0.5. So please don't think that it's always, those two numbers are always the same, because for doxycycline, it's going down 30%. Now, you can, even though it asks you one question first and the other, like I could find that, remember how we can find the decay factor is we can do, I could do 70 divided by 100. This would be the decay factor, 0.7. But if the decay factor is 0.7, then that means we took off 30%. So then 30% is how much it degrades. And because these numbers were kind of easy to work with, we might have just recognized that that's going down 30% because it's easy to figure 30% of 100 is 30 and take it away makes 70. So if we want to write the equation, our equation, we have two different equations down here to write. Just put a y equals in front of what I have written up there basically. And plug things in, of course.
Miss your family.
I know, I'm going, it makes me a little crazy here. Okay. I can't write with the mouse though. It's just not, it's not pretty. Okay, so for amoxicillin, y equals, how much do we start out with? 500. And then 0.5, because it's 1 minus 0.5, so the decay factor is 0.5. And then, so that just any hour, we would just leave that as an X. What's going to change? Well, we have a different initial amount. This would just be 100. And then this is the one, this is our 0.70. Or 0.7 would be the same. And sometimes you'll see, and sometimes even like on my paper, I use T instead of X just to remind me that it's time. And so if you wanted to check your formula, if you have this table, if you put in a 9 for T or for X, then you should come up with what's in the table here. In fact, they've given to lots of decimal places. So we can see that the medications are going to lose their effectiveness over time. What do you think? Would it be acceptable to come up with a medication that once you take it, it remains active indefinitely?
I think it must be a vaccine.
But a vaccine even doesn't. Although some vaccines last longer. I mean, like we don't get measles vaccinations over and over when you're an adult.
That shot, you get 3, and then after that, they say you never need another one.
There's even a booster for that. I think it's like every 10 years.
Guess not.
So But medication and vaccination is not quite the same thing.
Like
Right.
polio.
Most
Once you take it.
illnesses, well, it depends on the illness that you're making. Some are like,
Well,
they stick with you for the rest of your life,
Health
some are
remedy.
just, quick fix.
Right, so like, if it's like, because I have a headache, I don't wanna just take something that has me medicated and not
Or-
feeling things
Yeah, and
forever,
then
like.
keep you medicated forever, even if you didn't take the medication, headache probably.
But I could see what you're saying though, too, that like, if it was something like,
like a
okay,
lot.
now I have
Like
diabetes, I have type 1 diabetes. And I want to regulate, but then my body's needs change with what I eat, so if I just took insulin that just stayed in my body forever. How rude. I'm sure it's been investigated, and there's some things like, how could that work?
Say no.
I think it would be dangerous to think it, because also if it remains active indefinitely, then when you take other things, if you had to take something else, then what it would interact with.
Never be able to drink again.
Wow.
What do we first number?
Don't take medications while drinking.
It's an opinion question, yeah. I just mean, like, you could make a case for,
Sorry.
Yes.
all right, new life forms. So how is the number of life forms changing from day to day? So use 2 of the consecutive data points. I think I heard someone say double it. Is it?
And 200%. And double.
Okay, so it doubles, so we could say it's doubling. But we would not use 1 plus 200%. We would just use a 2. Right, so it's increasing by 100%. So if something is doubling, it's like 200% larger, but it's increasing by only 100. Don't add an extra 100 by using 2 with the 1. So we could simply say it's doubling. That would be in. So the initial value. What's the lowest number? What on day 0? 40. And in this case, we've had a lot of years, but this time it's days. And then here, if we construct a model that predicts the number of life forms given the number of days since discovery, we've got our initial 40. And then when we do 1 plus the 100%, or if something is doubling, it's just a 2. And then this would be my X or my days or D or whatever I want. Now, if you've had algebra 2, this is where logarithms and change of base would come in to determine the exact time. But that's not part of the realm of our class. And so we are just, and this is what it says, it's not just me, it says use guess and check. When do you think it's going to get to 2000? And we can already see it's already at 640. So we're just guessing and checking. When do you think it's going to get past? What's the first day? Yeah, so at day 6. So at day 6, we are at 2,560, but that's the nearest whole day. So when it says use guess and check, you're just putting in different numbers. Obviously, don't try something smaller than 4 because those numbers are already here. So consider the numbers that you already have so that you don't just, your guesses are good so that you don't have to guess and check too many. we have talked a little bit about this situation, that some technology, the prices actually are going down. So this is decreasing. So since it's decreasing, is it exponential growth or exponential decay? Decay, yes. So now we're going to construct a model. Sounds like we're going to build stuff, but not quite. So we could say that our cost equals, or you could use Y. Our beginning is 1,500. And then if it's decreasing at 15%. So what are we going to put in here? 0.85. So 1, take away the 15%. So like if I want it next year, I could just do 1,500 times 0.85. And then, and this would be a number of years. So how many years will it take the TVs to be half of their original cost? Between 4 and 5 years, yes. And Randy, did you just experiment with a few numbers there?
Yeah, I just did 5 the first time and 4 the second.
Good. So if we did, and so we would be looking like we want it to come out to be 750, right? That would be half. So this would be, again, if we're looking for the time without using logarithms, then we are at a guess and check. Guess something, see where we're at. Guess something else, see where we're at. So if I did, if I only did 3 years, it's not enough. I did 4 years, not quite enough. 5 years is over. So somewhere between 4 and 5 years, or if I could just say 5 years, because then it's, but it's going to be less than half by that point.
I don't know, the price of 8K TVs, I think we're gonna have to wait a few
Ooh.
decades.
I've got 4K right now.
4Ks are super nice, but 8K is like, oh, man, you must be really hacking some hardware to make it run. Computer.
So pay attention to the wording to decide if it's growth or decay. Depreciates. So depreciates means the value is going down. So this is decay. And then don't forget, this is 1 minus the 0.12. Don't just use the 0.12. We're going to get a very different answer if we just use 0.12. So typically this is something I kind of do in my head. Like think of 100, take away 12 is 88. So make it 0.88. I do not do this stuff in my head though. Times 0.88. I know, what a slacker. And then, how dare they let me teach you? Who are they trusting with your impressionable minds? I've had some teachers who maybe they could have done this in my head. The problem then though was they could not explain anything. They were like, undoubtedly they were extremely bright.
In
And
a way, you can have practices to do some skill, like for me, for example, like I'll be playing a video game and my buddy will be like, okay, how do I do this move? It's like, you have to think about it because you do it naturally. You just-
right.
Yeah.
That was how I felt when I taught my daughter how to drive. You know, like I've been driving for so long.
Yeah.
And I said, people are like, you're paying for driver's ed? And I was like, yes. I'm paying for driver's ed because I don't want to have to ride her butt about studying. She just goes to class and she'll do what she has to do. And I wanted her to get some practice with someone who knew what specifically to tell. I was afraid I wouldn't tell her all the right things to think about, then I'd just get frustrated with her. It was stressful enough just practice driving, to be honest. God bless everybody who has to practice drive with someone. So how much did you guys come up with here? 13,193.30.
You round the 29 cents?
Yes. So if we're talking money, we're gonna round it to the nearest cent when we're doing these problems. If we're talking like how many animals, how many people, we'll round it to the whole number. Okay, go ahead and see what Michael has here. Notice that is not a misplaced decimal. That is, there are 2 zeros. It's like 0.3%. Not even, it's not 3%. So that answers your question actually for C. The monthly interest rate is 0.3%.
That's all.
Well, that is actually maybe generous compared to a lot of savings accounts right now. Decay, exactly. Yep. So if the number's gonna be going up, it would be growth. If it's going down, it would be decay. And if you see it's already written for you and you see it's greater than 1, yes, it would be growth. May not be very fast growth in this case, but it is growth.
Inflation.
I mean, but it's still growth. So then does that mean I shouldn't save any money, Mohammed? I should just go out and spend it all because inflation.
You should invest in the stocks.
That was my great grandfather's philosophy too.
Like spend it.
No, you're only gonna live once. What's the point of having a bunch of money when you die? My grandma told me that her dad would just spend everything.
Probably a generous man.
I mean, I'm pretty sure he didn't start spending everything until he got to the older years, but at that point, like everything was gone. Crazy.
So how much is in the account after 6 months? Notice this gives us the entire amount in the account. It doesn't give us how much interest he makes. 992.68. 992.68. Again, they already wrote the equation at the top. We're just putting a 6 where they had the M for months. What about after 12 months? Double that. He wishes. Yes, $1,010.68.
Years to get to 2,000.
It just asks when he's gonna get to $1,000. Now, let's think about, here we're supposed to guess and check. How long will it take till he gets at least $1,000? Aren't we already over $1,000 at 12 months? Well, but
no.
could it be sooner than that? We need to guess and check and find out when it happens sooner than that. So what's the first month that it ends up over 1,000?
9, 11,
9, yeah.
10,
11 is also over.
Uh-huh. I went down from
9 is the first one. Yes.
Oh.
Yes. So that would be an experiment question. But please, if you've already figured out for 12, don't go higher than 12, but you need to check to see how low you could go. Logan. Yeah. Okay, turn about, I don't know, 6 or so pages. And spend the next 15 minutes working through some of the homework things, and then we'll do more examples. We have a nice Futurama question, if anybody's a Futurama, anybody knows about that, there's a nice,
Shiny metal.
there's a nice question about, a nice little scenario about something mathematical that was brought up in the cartoon, and if it's true or not. So there are two different, we have not talked about the simple interest rate yet, so don't try the second one, just try things on the first one.
Just making sure for the one we just did, the monthly interest was 1.0, right?
The monthly interest you would just say is 0.3%. And actually that is way higher than it is now, because that's expressed monthly, not annual. So that ain't happening. So you can use your new remember that new over old would give you the growth factor, and then you would have to subtract 100% off of that. Or you could do the difference over the old. For number one about the raccoons. So the growth rate is just the percent of increase. You would take how much it's changed, divide it by the number of raccoons. Yes, good. For scientific notation.